SpaceX has been quietly dropping an avalanche of new footage, fresh flight data, and hardware updates through the week following Starship Flight 13, and once you actually dig into the numbers, the performance gains buried inside that data turn out to be far more interesting than most people realized at first glance. On top of that, there are new hints emerging about when Flight 14 is actually coming, along with a packed stretch of news covering Blue Origin, a serious setback for the mission tasked with boosting NASA's Swift Observatory, and a long list of other developments across the industry. If you think you already saw everything Flight 13 had to offer, it's worth looking again, because a huge amount of new material has surfaced since that launch actually happened. Flight 13 concluded with a long list of improvements over the very first version 3 flight test, Mission 12, and the fresh footage SpaceX has released since then, much of it in full quality and previously unseen, gives a far more complete picture of exactly what happened during that flight. The most useful way to work through everything that's come out is to follow the actual timeline of events as they occurred during the mission itself, starting with liftoff. SpaceX released multiple slow-motion angles of the initial launch, and from a distance, one of the clearest details is the water deluge system kicking in from the top of the launch deck the instant the engines ignite. The original Pad 1 was built around the idea that the pad's floor would simply deflect the raw energy produced by 33 Raptor engines. The newly built Pad 2, with its considerably larger flame trench, was designed to do something fundamentally different, and the footage confirms it works exactly as intended. The moment those engines ignite, the enormous thrust and fire that would otherwise be a steel-melting force lancing straight downward gets almost completely converted into steam, violently but harmlessly ejecting outward from both directions of the new flame trench. Watching the shock waves ripple through the exhaust plume in slow motion makes the scale of that energy conversion even more obvious. The rocket itself weighs somewhere around 5,000 metric tons, and those 33 Raptor 3 engines lift that entire mass off the pad with a smoothness that looks almost effortless on camera, despite the sheer violence of what's actually happening underneath it. In one wide shot, the exhaust briefly fills the entire frame, highlighting the launch site in front of it with the old Starhopper prototype, the same small test vehicle that flew its 2 test flights more than 7 years ago, sitting quietly in view as it watches yet another Starship head toward orbit. A closer camera angle gives an even better look at the engines themselves. The small clouds visible pouring off the sides of the super heavy booster come from cryogenic oxygen filling the massive bottom tank, creating a solid layer of frost on the tank's exterior that gets rapidly stripped away and pulled into the exhaust plume as the vehicle climbs. Even zoomed in fairly tight, it's possible to make out where the combined exhaust from all 33 Raptor engines merges into one enormous Mach diamond pattern, the interlocking shockwave structure that forms when exhaust flowing faster than the speed of sound interacts with the surrounding air pressure. An aerial drone view adds yet another perspective, this time showing the dual exit flame trench from above in real time, and it gives a genuine sense of just how much higher the thrust-to-weight ratio is on version 3 compared to version 2. One of the stated goals of Flight 13 was to push the vehicle through higher dynamic stresses than any previous flight, specifically to test how the heat shield would hold up under those tougher conditions, and that test was confirmed successful. Beyond the qualitative footage, there's also hard data worth walking through carefully, because Flight 13 clearly accelerated faster than Flight 12, and comparing the last 3 flights in detail reveals exactly how much faster. Flight 12 and Flight 13 track each other extremely closely in speed, right up until roughly the 48-second mark, right around the point where Flight 13 approaches maximum dynamic pressure. From there, Flight 13 pulls away noticeably. By 80 seconds into the flight, it's already moving more than 330 kilometers per hour faster than Flight 12 was at the same point. Compared to Flight 11, the last version 2 Starship Flight, the gap is even larger, with Flight 13 already close to 750 kilometers per hour faster by that same point in the ascent. That widening speed advantage over Flight 12 continues to grow all the way through to the 2-minute and 8-second mark, at which point the gap stops expanding. That plateau is itself a useful data point because in both Flight 12 and Flight 13, SpaceX appears to throttle the engines down slightly around this stage of ascent, even though every engine remains lit through this phase. That throttling suggests there's still real performance margin left in the vehicle that simply isn't being used yet at this stage of the flight. The engines are eventually extinguished around the 2-minute and 18-second mark. There's also a smaller but still notable difference in altitude. Flight 13 reached a clearly higher altitude than Flight 12 at the point of stage separation, and the size of that gap is almost identical to the altitude advantage Flight 12 had over Flight 11, an increase of roughly 4 to 5 kilometers each time. One detail missing from the original live coverage was an external view of the hot stage separation captured directly from the ship's own camera. SpaceX had already released footage of that moment from the Super Heavy's perspective shortly after the flight, but a newly released still and video from the ship's own point of view fills in the rest of the picture. That footage shows the upper stage's exhaust flowing across the length of the booster as it flips around to begin its boostback burn, with all 33 engines firing to reverse the booster's direction. Zooming in and slowing the footage down further reveals the ship itself briefly getting caught in that exhaust plume as it pulls away from the booster. When the live feed switches back to the external camera mounted on the ship after hot staging, the steel of the vehicle is visibly changing color along its sides, a rainbow-like effect caused by the tempering of steel when it's exposed to extremely high temperatures. That effect becomes even more visible later in the ascent, once the area is lit up properly by direct sunlight. Once the flight reached the payload deployment phase, SpaceX released what might be one of the most striking pieces of footage the entire Starship program has produced so far. The clip shows the deployment sequence from the Starlink satellite's own point of view as it slowly drifts away from the ship, built as a composite view combining 4 of the satellite's onboard cameras into one continuous shot. As the ship's flaps give a few small wiggles, it performs a slow spin, giving the cameras a full 360-degree view of the vehicle's exterior, including a clear look at areas where missing heat shield tiles were deliberately left off as part of an ongoing tile durability test. The ship then fires its reaction control thrusters to move further away from the newly deployed satellites, part of the standard preparation before the in-space engine burn ahead of re-entry. During that same window, cameras also caught a glimpse of the satellites themselves opening their solar panels while Starship performed its in-space Raptor relight. But since then, SpaceX has released a set of genuinely remarkable real photographs taken directly from the satellites. One image shows multiple satellites side by side with their solar arrays fully deployed, and the satellites on the right appear to be actively test-firing their Argon Hall thrusters, the electric propulsion systems that will eventually be used in full orbital operations to maintain and adjust each satellite's position within the constellation. This marks the first time a Starlink satellite has been observed firing its thrusters while still in view of the deploying ship. A second image, taken from one of the satellites looking back toward the ship, shows the vehicle partially lit by onboard flashlights carried aboard some of the satellites, a perspective that would likely look even more dramatic once Starship is captured in full daylight during a future flight. Going back to the in-space engine relight itself, a number of ground-based spaceflight enthusiasts were watching for visible signs of the burn from Earth, and one observer managed to capture the relight from Johannesburg, South Africa, where it was clearly visible from the ground. It's worth being precise about what's actually being seen in footage like that. The visible light isn't coming directly from the engine itself, but from the interaction between the engine's exhaust and the surrounding atmosphere as the plume is thrown into it at nearly orbital velocity, producing a brief but genuinely striking light show visible from the ground at the right location and the right moment. After re-entry, SpaceX also released cleaner footage of the final landing sequence, followed by the now familiar flip maneuver. That entire sequence happens quickly. The engines fire, the vehicle flips around within seconds, and as it gets closer to the water, precise thrust vectoring from the 3 central Raptor 3 engines guides it down to a remarkably smooth splashdown. A drone view of the landing, captured with the drone's own rotors still visible in frame, gives a genuinely striking full perspective of just how soft that splashdown actually was, catching many observers by surprise. SpaceX also released a newly captured photo of the vehicle just before splashdown, along with a full uninterrupted angle of the entire landing sequence from the ship's own onboard camera. Following the success of Flight 13, SpaceX confirmed that its next mission, Flight 14, will attempt something the entire Starship program has effectively been building toward from the very beginning, a tower catch of the upper stage itself. Midweek confirmation revealed that the ship from Flight 13 was actually controlled precisely enough during its final approach that a tower arm catch could realistically have been performed had one been attempted. That milestone is expected to be paired with a fully orbital Starship flight, presumably placing a version 3 Starlink satellite payload stack into an actual operational orbit for the first time. There's also an update on the fate of the ship that splashed down after Flight 13. After it was left bobbing in the ocean, there was some speculation about whether SpaceX might attempt to recover it, and that speculation turned out to be accurate. The Starship recovery team stayed with the vehicle for days, gathering imagery of it, still afloat in the Indian Ocean, and SpaceX later announced it was sending an additional ship out specifically to bring it back. Exactly what back means in this case is still an open question, whether that involves returning it to shore somewhere in Australia or attempting to transport it all the way back to Texas, and further details on that recovery effort are still pending. With Flight 13 fully covered and its aftermath still unfolding, the next obvious question is how far away Flight 14 actually is. The Starship assigned to that mission, Ship 41, appears to have had all 6 of its Raptor engines installed in the back left position inside Mega Bay 2, which suggests it should be rolling out for its static fire campaign relatively soon, likely within the next few weeks. Because Flight 13 was a clean success, there's no FAA investigation required this time around. removing one of the more common sources of delay for a mission like this. Current indications point toward a target flight date sometime around the 20th of August, putting the rough month-long window currently being discussed on reasonably solid footing. The Super Heavy booster assigned to that same flight, Booster 21, should also be rolling out for its own static fire testing over a similar timeframe. In preparation for the planned tower catch attempt, SpaceX has also been seeking approval for additional landing abort zones, covering scenarios where the ship is unable to perform a planned catch for any number of reasons. In that situation, the plan calls for Starship to perform a de-orbit burn and target a splashdown in the North Pacific, off the west coast of the United States, specifically to avoid any risk of debris coming down over populated land in the event something goes wrong during the catch attempt. It's worth pausing on why the flame trench comparison between Pad 1 and Pad 2 actually matters so much, because it's easy to treat it as a minor engineering footnote rather than what it really represents. The original approach at Pad 1 assumed the pad's steel-reinforced concrete floor, cooled by a dedicated water deluge system, could simply absorb and deflect the raw energy of 33 simultaneous Raptor engines without a purpose-built exhaust channel underneath. That approach worked, but it came with real costs, including damage to the pad surface after early flights that required repair work between launches. Pad 2 represents a fundamentally different philosophy, one built around actively channeling that exhaust energy away from the pad structure entirely, converting the raw thermal and kinetic force of the engines into steam that vents outward through a dedicated trench, rather than fighting to contain or deflect it in place. The fact that post-flight inspections keep turning up only minor, cosmetic-level wear rather than structural damage is a strong signal that this design philosophy is working as intended, and it matters enormously for the pace of the overall program, because a launch pad that survives each flight with only superficial scorching can support a much faster turnaround between missions than one requiring significant repair work after every use. The heat shield test conducted during Flight 13 deserves a similar level of attention, because surviving higher dynamic stress during ascent isn't simply a matter of the vehicle not breaking apart. It's specifically about validating that the thermal protection system bonded to the vehicle's windward side can handle a wider range of aerodynamic loading than previously confirmed, which directly expands the range of trajectories, payload masses, and re-entry profiles. The vehicle can be trusted to fly in future missions. Every previous flight has effectively been chipping away at a list of unknowns surrounding how this specific heat shield design behaves under real flight conditions, rather than in a wind tunnel or a simulation. Confirming a successful result under intentionally harsher stress conditions closes off one more of those unknowns. And that kind of incremental validation is precisely what has to happen repeatedly before a vehicle like this can be trusted to fly a fully orbital mission with a genuine, reusable payload stack aboard it. The tower catch milestone being targeted for Flight 14 sits on top of all of that validation work. And it's worth being clear about just how significant an attempt like this actually is within the broader logic of the Starship program. Catching the upper stage with the tower's own arms, rather than relying on legs or a separate landing structure, is central to the entire reusability model this vehicle was designed around, because it removes the weight, complexity, and turnaround time associated with a traditional landing gear system entirely. The fact that Flight 13's ship was reportedly precise enough during its final approach that a catch could genuinely have been attempted is a meaningful signal on its own, independent of whether SpaceX chose to actually attempt it this time. It suggests the guidance, navigation, and control systems responsible for bringing a vehicle this large down to a specific point, with the kind of precision a tower arm catch demands, are already performing close to the level required, which is exactly the kind of confidence a team needs before committing to attempt something this unforgiving for real, with no fallback landing option built into the plan beyond a controlled splashdown if the catch has to be aborted. Aerial photography taken shortly after the launch shows that Pad 2 came through the flight in solid condition. There's a slightly scorched area in one corner of the top deck near the individual holes where deluge water exits the structure, but nothing about it currently suggests a serious concern, and it's the kind of detail the pad team is almost certainly monitoring closely regardless. If that section of plating does eventually need modification, it's a fairly straightforward fix. But beyond that superficial discoloration, the rest of the pad shows no other significant signs of wear, suggesting Pad 2 continues to perform exactly the protective role it was designed for. Pad 1, meanwhile, is being rapidly upgraded to match. The commodities bunker, which had been pre-assembled off to one side, has now been lifted into its final position, where its multiple levels will eventually be fitted out with the hardware needed to fuel a super heavy booster. Excavation of the flame trench itself is now fully complete, and the first layers of leveling concrete are being poured to create a clean working surface. That allows crews to begin cropping the tops of the support piles to expose the rebar underneath, rebar that will eventually tie directly into the foundation of both the flame trench and the launch mount. Work on that process has already begun along one side of the trench. Nearby, the trench's sidewalls, which are being pre-welded off to the side before installation, have now reached their third level of construction, considerably further along than expected at this stage. Once those wall sections are ready to be lifted into place, the assembly process is expected to move quickly. Crews have also started assembling the support frames that will hold the deluge piping above the trench, and once those frames are fully welded together, the flame bucket halves themselves will be lifted into position. Delivery of additional launch mount components has also resumed, including one of the corner sections needed before the bottom section of the mount can be fully welded together, a piece that several other components have reportedly been waiting on for some time. Higher up, the tower arms remain surrounded by scaffolding as part of an ongoing round of cleanup and upgrade work. Among the more significant pieces of that effort is a new home for the Drawworks hoist system, the mechanism that allows crews and equipment to move up and down the tower, since its previous housing was removed before this round of upgrades began. Sections for that new housing have now started arriving on site, suggesting installation should follow relatively soon. Separately, removal of the last remaining section of the ship's quick disconnect arm got underway this week. The arm was hooked up to a crane and prepared for removal over a weekend, with cutting work beginning the following day. Once lowered to the ground, the old structure was quickly broken down with excavators, since none of it was suitable for reuse, and cut into pieces small enough to be hauled away in bins. Sections for a full replacement arm are already sitting in a nearby staging area, expected to be assembled soon, and by most indications, the new design should closely resemble the version already installed on Pad 2, a noticeably cleaner and more organized layout than what it's replacing. There have also been a few notable developments at the nearby structural test site, the B-18. 3 test tank was finally removed from its cryogenic test rig after roughly 20 rounds of testing, freeing that equipment up for a brand new nose cone test article that has since rolled into Mega Bay 2. That same nose cone had previously been spotted under construction, fitted with a number of extra external attachments and ports. It isn't yet clear exactly what that hardware is meant to test, but given how long it's been since a dedicated nose cone test article was last put through this kind of testing, it seems likely the goal is a broader structural evaluation of the nose section under the latest vehicle architecture. Separately, an earlier test article has now been removed and returned to a nearby staging area, clearing more space for whatever comes next in the testing queue. On the Falcon 9 side of the business, there's been a steady cadence of activity as well. One mission lifted off from Vandenberg Space Force Base under clear skies, carrying 24 Starlink satellites as part of a numbered mission group. The booster flying that mission was only on its 8th flight, and it landed successfully on a drone ship stationed off the California coast shortly afterward, with SpaceX releasing a striking deployment shot showing the sun low on the horizon in the background. A second Starlink mission followed just hours before this update, also launching from Vandenberg, this time using a considerably more experienced booster already well past its 20th flight, landing on that same drone ship, which remains the only recovery platform currently available for missions launching out of California. A separate Falcon 9 mission launched from Florida, flying a booster on its 7th flight and carrying another confidential payload for the National Reconnaissance Office. That mission used a return-to-launch site profile, meaning after stage separation, the booster performed a lengthy boost-back burn to bring it all the way back to the coast, rather than landing offshore. Because the return happened in darkness, the descent was harder to see clearly on camera, though a brief flash of color was visible immediately after touchdown at the landing zone. There's also been meaningful progress on the Blue Origin side of the industry. At Launch Complex 36, the team has now fully destacked the top 6 sections of the vehicle access tower. Rather than immediately rebuilding it, engineers are using this window to integrate new fluid lines, cryogenic systems, pneumatics, control hardware, and updated access floors needed to support a new hybrid horizontal and vertical processing system. Carrying out that work while the tower sections are still on the ground allows multiple systems to be worked on simultaneously, which appears to be the only realistic path toward meeting an end-of-year target for the next New Glenn launch. Because the pad itself isn't currently available for hot fire testing, Blue Origin has also signed an agreement with NASA to conduct New Glenn's second stage hot fire testing at the B-Test complex at NASA's Stennis Space Center, a historic test stand that was originally used to test the first stage of the Saturn V rocket, and later the main propulsion test article for the Space Shuttle program. That same facility will now support testing for New Glenn's upper stage. On a related note, there's also fresh footage of a new lunar rover being tested by Honeybee Robotics, a company owned by Blue Origin. That rover is scheduled to be delivered to the moon aboard Firefly Aerospace's Blue Ghost 3 lunar lander, currently targeted to launch in 2028. Once there, it's expected to explore the Gruithuisen Gamma Dome, one of the moon's more unusual and largely unexplored volcanic regions, spending roughly 14 days traveling across the surface while carrying a set of NASA instruments designed to study the dome's composition and help explain how these unusual volcanic formations originally formed. Honeybee Robotics has now completed its critical design review for the rover, clearing the way for full flight hardware production to begin. There's also been a notable conclusion to the latest International Space Station crew rotation. After the newest Soyuz crew settled into its routine following launch a few weeks earlier, it was time for the station's previous Soyuz crew to head home. That spacecraft undocked from the station's Rassvet module carrying a NASA astronaut, alongside 2 Roscosmos cosmonauts. Following a deorbit burn several hours later, the crew completed a textbook parachute-assisted landing, closing out a mission that lasted 241 days in total. Over that span, the crew orbited Earth 3,856 times, and the mission marked the first spaceflight for 2 of the 3 crew members involved. Unfortunately, not every story from this stretch has gone smoothly. The mission tasked with boosting NASA's Swift Observatory has run into serious trouble. A commercial servicing spacecraft launched at the start of July experienced attitude control issues during its commissioning phase, entering an uncontrolled multi-axis spin that temporarily knocked out communications and forced a full reset of its onboard systems. Since then, the spacecraft has also lost 2 of its 3 reaction wheels and is now operating with only partial reaction control thruster capability, a genuinely serious setback for the mission. The situation isn't considered a total loss, though. Engineers are using the spacecraft's gimbaled electric propulsion system to slowly stabilize it, with the eventual goal of still attempting the planned rendezvous and capture with the Swift Observatory. It remains a significant setback, but the team involved still believes that rendezvous and capture may ultimately be achievable, and the effort to save the mission, and by extension, the observatory itself, is continuing. There's a broader competitive context worth understanding behind Blue Origin's tower rebuild timeline as well. New Glenn represents the company's first genuinely orbital-class vehicle capable of competing directly with Falcon 9 for a meaningful share of commercial and government launch contracts, and every month of delay on ground infrastructure translates directly into missed manifest opportunities in a launch market that has become considerably more competitive over the past several years. Choosing to destack the tower entirely, rather than attempting to retrofit new systems around an assembled structure still standing at height, is a genuinely aggressive scheduling decision, since it means the pad is completely unusable for any launch activity during this entire window of work. That kind of decision only makes sense if the alternative, working around a fully stacked tower piece by piece, would actually take longer overall. Borrowing NASA's historic Stennis test infrastructure for upper stage hot fire testing in the meantime is a pragmatic solution that keeps the vehicle qualification schedule moving even while the home pad remains offline. And it's a reminder that even a company building entirely new orbital rocket hardware still depends heavily on decades-old government test infrastructure originally built for an entirely different generation of spaceflight. The Swift servicing mission setback deserves a closer look too, because it illustrates just how unforgiving the early commissioning phase of any spacecraft can be, regardless of how much ground testing precedes launch. Attitude control issues serious enough to trigger an uncontrolled multi-axis spin represent close to a worst-case scenario for a freshly launched spacecraft, since a tumbling vehicle can't reliably point its solar arrays at the sun, can't maintain a stable communications link, and can't safely fire any of its propulsion systems until the spin itself is brought under control first. Losing 2 of 3 reaction wheels on top of that failure compounds the problem significantly, since reaction wheels are typically the primary, most fuel-efficient method a spacecraft uses for fine attitude control, and falling back on electric propulsion for stabilization instead is a considerably less precise, more fuel-intensive workaround. That the mission still has a credible path toward completing its rendezvous and capture objective despite all of that says a great deal about how much redundancy modern spacecraft are designed to carry. But it also underscores just how much has to go right in sequence, stabilization, propulsion management, precision approach, and physical capture before a servicing mission like this can actually deliver the outcome it was launched to achieve. A successful reboost would extend the operational life of an active NASA observatory that would otherwise face a much shorter remaining lifespan, which is exactly why the team continues pushing forward despite a setback serious enough that many missions might have been declared a loss at this stage. Of an industry moving on multiple fronts at once, a Starship program racing toward its next major milestone with a tower catch attempt now openly on the table. Pad infrastructure on both coasts being rebuilt and upgraded in parallel, a steady rhythm of Falcon 9 missions continuing largely unnoticed in the background, a competitor rebuilding critical ground infrastructure under a tight deadline, and a servicing mission fighting to recover from a serious in-orbit failure well before its primary objective has even been attempted. Each of these threads is moving at its own pace, but they're all unfolding at the same time, across the same few months, in an industry where the gap between one major milestone and the next keeps getting shorter.